All right, welcome to the final lecture here. So we're going to be talking about the topics. I'm going to just pull it all together, try to make this into a concise uh, one big whole course so that you understand. Well, it's a tall order. Not sure if you will, but let's see. So we started talking about this topic with the idea that we talked about probability and what it means that something has a probability. That's really, really important to understand that probability can be interpreted in one of many ways. We don't take any particular view on how you should interpret it. I'm not claiming that probability is this or probability is that, and that, you know, for example, I'm not claiming that probability is by nature something that we don't know, and then we just use that measure of probability as some kind of a level of uncertainty. That's definitely a coherent view of probability, but there are alternative ways of looking at it. I mean, philosophical questions such as, you know, are there truly random events in the real world? Not making a claim about that either. We are only interested. This is a model of how certain things that seem to happen in different ways depending on when you measure them. So if you roll the dice, you sometimes get a 1, a 2, a 3, or 5, or 6, right? And that's, you know, probabilities is a way of capturing this idea that the result can be one of many things and you just don't know what it is beforehand. Whether that's due to some uncertainty or inherent randomness, something that, you know, things actually happen in a random way, that's not a concern of us. And at the beginning, we had this model. We talked a lot about that, and there were definitely something like a deck of cards has 52 cards, and then they have suits, 1 of 4, and cards with numbers either from 1 to 13 or 2 to 14, and you know, you shuffle them and you get some random card. One of the cards on the top is one of the random ones. So these were simple models, a model of randomness, also rolling the dice and so forth. So we had the idea or the concept of a sample space and an event. So you know, the event can be characterized as one of the things that is possible as happening and has some property related to that thing. So just to give an example, let's say I roll a die, I get an even number. So I roll a die, it's got numbers from 1 to 6, and there's 2, 4, and 6, which are even. And we talked about the idea of classical probability. So the idea of classical probability is that we assume that all of them have the same probability, you know, the same likelihood, or you know, they happen in the same way. So every one of the 6 numbers has 1/6 probability, and when you roll the die and you get an even number, 1 out every other time on average. But this is just the concept of probability. But what does it mean? So we had this idea, which is the so-called frequentist idea. So the frequentist idea is that we define the probability measure, which is not the probability measure yet, like this Pn of A. So it's the rudimentary or relative frequency of event A. So we calculate how many times this event A happens over n executions, and then the probability, statistical probability of A is the limit of this Pn A as n approaches infinity. But this is highly unsatisfying. I mean, it's philosophically pleasing in some sense to some people, not everyone, but it's highly unsatisfying mathematically, because if you think about this, it doesn't say anything about how fast it converges. So the first million, I mean, let's say you toss a coin. So the first million coin tosses may be heads, and it's perfectly consistent with this. And there's nothing to say that that's even an improbable situation. It's just that if you throw it infinitely many times, then half of the tosses on average tend to be, at the limit, half of those in the infinite sequence are tails and half are heads. So it's not very it's not very informative as a concept of probability, but it is still essentially how people often view this idea. So the frequentist approach works in this way. So just carry the experiment, the weak frequentist approach is that you cannot say anything, and then the stronger frequentist approach is that, if n is large enough, then you know that this tends to be very close to the actual average. And that's how we tend to think of this in practice. The alternative idea, I accidentally, what? Oh, I accidentally pressed the wrong button here. So the alternative was thinking in terms of classical probability, but classical probability is just that you have certain atomic cases like numbers in the die, and your event is, how many of those atomic cases correspond to your event, let's say even numbers, and then divided by all cases, which in this case is 6. So there are 3 cases of even numbers and 6 cases of possible numbers. So it's 1/2 the probability of getting an even number. But real life applications are generally not equally probable, and it's when we're talking about numerical values, it's very often very, you can't come up with a situation like this. There's often combinatorics involved, and this is why some people find this classical probabilities thing both tedious, I do at least, and hard mathematically, because combinatorics is quite hard. So we don't deal with that all that much, although it is a fruitful way of coming up with certain probabilities of things. So here were some of the combinatorics. I'm going to skip that. We're not going to talk about this today. Just a way for you to consider these probabilities. They come into play in different places, like computer science, cryptology. They come into play in places like games and things like, restricted situations. Then this is definitely something that is worth learning. So here we come with the axioms of probability calculus. So we had what is called the sigma algebra. We didn't have to worry about that all that much, but it's just that if you think about this in terms of later when we talk about normal distributions and so forth, then what the sigma algebra here are sets over which you can integrate. And then the measure is the integral, and then you have this probability measure, which was one that follows the Kolmogorov axiom. So the probability of any event is between 0 and 1, and then it's additive. So if you add disjoint events, then you add their probabilities, and the probability of getting something is 1, and the probability of getting nothing is 0, right? And that's about it. But you can think of this as just, we discussed this, but you just should be there in the back of your mind, so that every time you discuss things, you should be able to return it into this. There were a lot of this, and then one really important part to understand is the conditional probability here, and this I wanted to spend a little bit time on today. So we remember that the probability of getting A under condition B, it's simply the probability of both A and B being true divided by the probability of B being true. And the thing about that, when we talked about hypothesis testing, then really the is P. So if say I'm writing this in the chat page. So if we say that we're going to have this we have these two hypotheses. We have H0 and H1. So these are two, you can think of this as these are two events. So which have already happened. So either the null hypothesis is true or the alternative hypothesis is true. We don't know which one. And we want to figure out which one of these is more probable. We have no idea about the probability of H1, but we have some idea of if H0 is true, then, well, and we have this S is the sample. So let's say the sample, and I'm just saying, this is the event that we got a certain sample, and in fact, this sample has certain properties, like for instance, the average of this sample. So we have the sample mean, for example. This could be the sample mean, but I'm just saying this is the event related to the sample. In terms of our test statistics, let's call this event S. And we want to define the S, so because it's S alpha. So it depends on alpha. So we are going to have a certain event. So it means that either it's in the critical region or not in the critical region. And what we really want is PS alpha if H0 is true, that it's alpha, right? This is what we want, right? So we have defined an event. This is sorry, let's call it reject. So if R is the event that reject, we want the PR under H0 as alpha, right? So if our probability measure, is, or the probability of rejecting, if null hypothesis is true, we get alpha, right? So this is something we can control. So we make the assumption that the H0 is true. It means that we have a certain whatever, the certain distribution, and we set the goal or the standard for rejecting. So we are going to make a random experiment, and R is the event that materializes when the value that we are calling the test statistics is in the critical region. And this is the core of it. So we get this probability of rejection if H0 is true is alpha. So what happens is we are going to be using the idea of conditional probability here. And the idea that we end up rejecting if H0 is true is going to be small. And now if we look at the conditional probability here, we have no idea here what the probability of if our B here is H0, we have no idea what the probability of H0 being true is. We don't know. We do know that we know this probability that this conditional probability that we know. So we will gain access to this, if you will. And then, but then we can assume that the probability of H0 is 1 minus the probability of H1. We assume that they're mutually exclusive, so either H0 is true or H1 is true. This is a tall order again, but you know, we will make this assumption. This is another assumption in the statistical testing. And then we can use the idea that we could calculate these conditional probabilities, then we can come up with the idea of the Bayes formula. Now, this Bayes formula talks about categorizing, and we have several possibilities, but in here we only have two. So what do we have? We have the idea of the Bayes formula, which says that basically this is let's focus on this. So the probability of the probability of H0 if we reject is, the probability of H0 times the probability of reject if H0 is true, divided by the probability of reject. Right. This doesn't give us much, but if we look at this probability of H1, then we already know this here that this doesn't give us anything, because we have no idea what probabilities of H0 and probabilities of H1 are. We have no idea. We're not equipped to deal with this with the Bayesian formula. And that's really important to understand. And when we talked about the statistical testing, so it's what we might call a purely frequentist idea. Many of the people who subscribe to the Bayesian idea or the Bayesian interpretation of probabilities, they tend to have this idea that statistical testing is nonsense as it's performed. Instead, you should have some prior probabilities ascribed to H0 and your null hypothesis and being true or false, and then you should update that based on how probable your sample is. And that's really something that I'm not going to deal with it here. I'm just saying that that's one avenue where you can go if you want to understand the idea of using probabilities a little bit more. And I do like this idea. It's not, my problem here with teaching this course is that I teach these statistical methods or the statistical testing the way the curriculum says it should be treated and the way it's done in practice in many fields. But you have to understand that in this sense, the methods that are being utilized, it's not written in stone somewhere, and then the scientists and people who do research are just, they just have to take it as given. Instead, you can make a difference if you learn better ways. This course is not, sadly, this course we didn't have this Bayesian approach to use it, to handling these samples and handling this statistical analysis. But it is an avenue that I do urge any one of you to study a little bit more, and I do find it to be at least for completeness sake and understanding the completeness of the argument. Okay, let's carry on. That's one thing I wanted to say about this. This Bayesian analysis is really very important to understand. So if you think about the quotient here, probability of B under condition A divided by probability of B, it represents the support that B supports provides for A. So if you think about the sample, then the sample provides some level of evidence for or against the null hypothesis, and the idea is that if this alpha is small, then it provides you with evidence for the alternative hypothesis, which is all the other things that have not been included in the null hypothesis. But it's impossible to assess the actual probability without having some prior idea of which one is more probable and what the probabilities are. And the Bayesian idea is to have an ascribed probability, or known as prior probabilities to those hypotheses, and then just use the samples as evidence for or against one hypothesis or another. So the idea that you simply accept or reject is not pleasing in many ways. Epistemologically speaking, epistemology deals with the I don't know how to pronounce that, but it's the branch of philosophy of science that deals with what we know. So if we just take a random sample and we get significance level of 95% and we reject the null hypothesis, do we now know that the alternative hypothesis stands and the null hypothesis is false? No, we don't know that. We have evidence to support the idea that the null hypothesis probably is false. But do we know it? No, we don't know it, but that's the idea. We should always think in terms of, not necessarily in terms of particular numbers, but in terms of uncertainty. We have a level of uncertainty. We may not have quantified the level of uncertainty at this point, but we do have it. That doesn't mean that it's operationally such that because anything can be true, we can do anything what we like. I mean, quantifying it makes it at least to some extent tangible, and it makes your decision process rational. But the thing is, one of the ways to think about it, and one of the ways it's framed in many places, is thinking in terms of bets. So betting. So if you think about betting for or against something, someone offers you, okay, I'll bet you $100 that, or 100 euros that this is the way it is. So you have to think in terms of, okay, how much am I willing to bet if I'm going to get $100 euros if that guy is incorrect, and this other, if the null hypothesis is rejected, I get 100 euros. How much am I willing to bet? So if the significance level is 0.05, if your alpha is 0.05, then you should be betting about 5 euros, right? 5 to 100. But that's it's something to think about and something to keep in mind. And you have to understand also that it's completely irrational to use this as an argument such that, okay, because there's an uncertainty here, then your guess is as good as mine. That's definitely not true. I got into this conversation a while ago. So there's this athlete. I'm not going to name them, but there was an athlete who was a little bit older already. They had not done very well when they were younger. They had competed and they had some trouble with their health. And then they this person made a comeback a few years after that. This was a sort of sports where not having a lot of body mass is a good thing, but you have to be strong, or you have to have a certain level of muscle strength to compete. So this person was much leaner, but still much more muscular and older, and a lot faster. So I said they are probably using performance enhancing drugs. And there were several things that were happening. This person's this athlete's performance was way beyond what they had performed younger when they tried to compete before. They had hired an Eastern European coach who had earlier some scandal involving giving performance enhancing drugs to their athletes, and there were all these other things that were kind of situational or you know, circumstantial evidence, things that go in the way that, okay, if this is a person who is using performance enhancing drugs, this is exactly what would happen. But of course, there were not proofs. And I said, I'm willing to bet that this person is using a performance enhancing drugs, but I mean, I can't verify it. If we come up with a reasonable way of verifying this claim, then we can come up with a bet. And this person said, this other person I was talking to said, why are you not giving this person a benefit of a doubt? Why would you assume immediately that they're using performance enhancing drugs? And I said, I'm not assuming they're using performance enhancing drugs. I'm simply stating that I find the probability to be high. So they asked what probability would I ascribe, and I said, I'd say the probability that they're clean is roughly 10% and maybe a 90% probability that they're using drugs. And they said, you can't convict someone in court with that kind of probabilities. And I said, definitely not. Definitely not. We have to be conservative with our null hypothesis. But I'd still be willing to bet 10 to 1 that they were using the performance enhancing drugs. So here's the thing that I'm getting at, is that if you view probabilities in a way that is rational, it will affect the way you think. If you view probabilities as simply, okay, it's not 1, so it could be anything, then you're not being rational about it. Okay, 50-50 probabilities are very seldom things that we come up with if we really think about it. So a person in their 30s making a comeback in explosive sports after having lost a ton of weight and still gained a lot of muscle, you know, that's possible, but you know, it's much easier when you're on drugs, right? So it's conditional probability at play. So try to cultivate this thinking in your mind. Not, of course, this having preconceptions about all athletes being on drugs. That's, you know, my prior probability for that is high. So that's probably why I came with these numbers. Okay, let's move on. Independence of events. That's another really important topic. We made a lot of independence assumptions when we did statistical testing and statistical analysis at the latter part of the course. And you have to understand that the independence of events is defined as probability of the events happening together is the product of the probabilities happening separately. That means that the conditional probabilities are not, I mean, having one happen has no effect on the probability of the other happening. So what's going on here? Why is this important? It's important because then if we take sampling, it was heavily, the random sample was heavily you know, hinges, or it was heavily built on the assumption that the different sample points are independent. So I gave an example of why this might not be reasonable. I mean, there's a lot of studies in psychology and fields like this, in fields that deal with human cognition and so forth, where the population of people who had been selected for the study had been really students of the person who was conducting the study. So if that's not, if those are independent of all the hypotheses that we are making, then no, that's not the case. So there's what is called the reproducibility crisis in many fields, especially in psychology, I think. So there's a lot of studies from the 60s and 70s that are now being found to be wrong. And the reason for that is that the studies were carried out with students. And the students are a selected population, and they're not, you know, when you select the students into the group, they're not actually even independent selections, because you pick volunteers. What they did was they would put a poster on the wall on campus, and they would say, okay, do you want to participate in this study? You know, come here and tell your friends. So the person who sees this visits their friends and says, look, we can make, maybe they were giving out movie tickets or free meals or something like this. Students are poor. They've always been poor, although I think modern day students are even poorer than they were in the 60s. But however, the point is that the sample consists of people who were selected not randomly from the population, so that each point is an independent manifestation from whatever the distribution is. Instead, people came, they told their friends came, and so forth. They had a lot of things in common with them, and the probability of picking one person with certain characteristics definitely increased the probability of another person having similar characteristics. So the random sampling idea that we talked about in statistical testing hinges not only on assumptions of normality of the distributions, but also on independently picking the sample. So that's really important to understand, and it's a whole field of statistics on how to do that. Again, you have to do a lot of assumptions and do a lot of experiments to come up with the measure of how independently they are picked and so forth. So we covered with these examples, and I'm not going to go there, but the independence here, it seemed remote at that time from a practice of using the statistics, and maybe you missed it when we talked about it, so I wanted to bring it here. So that's really important for future reference whenever you're using these methods, then please be aware of this phenomenon. Here were some calculations or computations. Then we moved on to talking about distribution. So the distribution was a tool. It had we had some things like we had that random variable, which is a mapping. So you really we associate the random mapping with the value, really. So let's say that our variable of interest is human height. So really the sample point is a person. You're picking a person and measuring how tall they are. But when you put them in a list, then you're really just recording the height, and you're looking at the average height or the deviation of the height, and so standard deviation of the height and so forth. So we do think of these two the same way. But I like you to think about this idea that what is the atomic occurrence. So if we're doing statistics regarding the behavior of people, then the atomic sample is a person. It's one person, and then the variables are like, who do they vote for, how tall they are, how much do they weigh, how much do they earn, so forth. Where do they live? You know, things like this. It can be something, anything like this. So, and then we have a mapping, like for instance, let's say we are reducing a person on how far do they live from the nearest hospital. So the person becomes one number, that's the distance to the nearest hospital. And then we're looking whether this distance and to the nearest hospital has an effect on mortality or when they have a heart attack. This could be a possible topic of research, something like this. One that we didn't cover that much, but you know, we didn't talk about regression analysis, which is sad because regression analysis is really, really one of the more important things. Another avenue which I implore you to study further is regression analysis. Single regression and multiple linear regression, nonlinear regression, multiple regression, really. And it's really highly important. Most machine learning, look, if you're studying machine learning and this deep learning stuff, really it looks like something else, but it's really nonlinear regression. You should understand it. It really is nonlinear regression. That's what it is. This neural network learning stuff, it's really what the neural network does is nonlinear regression. Now I'm not going to go there. It's definitely studying statistics and studying these topics is something to consider if that's the sort of thing that you're studying. There are a lot of students of machine learning stuff, and for them it's really important. This doesn't seem directly applicable there, but building a foundation of mathematics of probabilities and statistics is really, it's definitely something that you should have if you are to be taken seriously in there. All right. Discrete distributions where it's either finite or countably infinite. So you can just list all the possible values like this from x1, x2 to so forth. So that's countable. I'm not going to go into the mathematics of numerable and you know, uncountable. That's not topic here. Probability density function in both the discrete and the continuous case. In the discrete case, it gives you pointwise probabilities. In the one thing to note is that in the discrete case, you do know that the f of x sum up to 1, and so you know that each of these f of x's will be smaller than or equal to 1. Smaller than 1 mostly. But then when we talk about the continuous distributions, I'm going to skip that because I'm going to talk about it now. When you talk about the continuous distributions, then in fact the functions only integrate from -infinity, or you know, this could be integral over this omega, and this integral over this omega is 1. So the function itself, the density function, can get values larger than 1, and often does if your sample space, if it's a big spike at 0, then definitely. I mean, think about the normal distribution. A 0, 1 normal distribution, not so, but think about with expected value 0 and variance of 0.00001. It's in the exponent. It's the it's the divisor, the sigma. So you get very large values at close to 0. Just bear in mind. All right, let's move on. If an event is considered to be an interval of real numbers, one can think of the probability event as the surface area of the curve drawn by the PDF. So that's really, I mean, that's very often the case when we had these figures like this. I had figures like this one. Sorry, I spilled some. I probably put my sandwich on top of it, so that's why. So, you know, we marked these areas under the curve. This was maybe the chi-squared distribution. So that's the probability. That's the blackened area there. That's the intuition we used a lot. I'm skipping most of this. We had some exercises, and I hope you learned from those. We had some examples like the exponential distribution. We had the uniform distribution. Then we talked about the functions of random variable. Not going to go in there in depth. How to come up with the density function for when you have this mapping y equals h of x and so forth. Not going to go in depth in here. I trust that you dealt with this in timely fashion when we talked about it, and then we can then just forget about it now. Not forget, but you know, not go through there. Vector distribution is very important, highly important, really. not dealt with here in a proper way, because I mean, when we start to talk about vector distributions of random vector, that's when it comes that's when we started talking about things like correlations and covariances, and that's and marginal distribution. So that's really, these are the marginal concept of marginal distribution is highly important. So if you have let's say, I gave an example with the height and weight of a person, and you have certain distribution for height, a certain distribution for weight, and you can think of them as having a certain distribution there, really nicely behaving. But then, you can't assume them to be independent. So, a person who's 120 centimeters tall is not going to weigh 200 kilograms, or the person who is 2 meters tall is not going to weigh 20 kilograms. So, they're not independent, these two variables. And we talked about this independence and so forth, different situations there. Really, the important part here was, let's skip there, when we talked about the expected value and variance. So we have expected value definition in discrete case, definition in the continuous case, analogous. Just a second. Sorry about this. So expected values in the continuous case was the one that we used more. Not going to go in there, just remember what they were. Things about variance. So if you multiply a variable with something, then the variance becomes multiplied by the square of that something. And if you add something to the variance, to the variable, the variance is unchanged. So if you move the distribution left or right, if it's a real value distribution, the variance doesn't change. In the vector case, we had this expected values and variances just like before. Sorry, we don't have the expected values necessarily for them. Yeah, well, in the vector case, we had a expected value of a function from the vector. So obviously it's hard to talk about the expected value of the vector itself, because you can't multiply here in a sensible way. There is a way of doing that, but I'm not going to go in depth here, and it goes off topic. So we simply had as an example, I gave the BMI of a person. So we can calculate the expected BMI, and the vector is the person's weight and height. So we can calculate the BMI of a person and then look at that and so forth. The thing to understand that if two variables are independent, then the expected value of the product is the product of the expected values, but it's not vice versa. We have situations where the expected value of the product is the product of the expected values, but the two variables are not independent. So this is a check with which you can often quickly show that, look, these two are not independent, but you cannot use this to prove that they are independent. And then there was the thing about covariance, and it's sad that we didn't have too much time to talk about covariance. We didn't use it in our statistical testing and so forth. That's a bit sad, because that's also something that we might want to do. Very often it's not very, the examples are a bit contrived when we talk about, has the expected value changed? Well, the best we could come up with was, does one have an expected value greater than the other? But really, very often what we are more interested in is, does this X have an effect on Y? So we would use things like covariance and those methods we didn't deal with. You don't have to worry about them, but be aware that similar methods or similar theory exists to do that thing using measures like correlation and covariance and to determine whether the two, to what extent the two are dependent on one another. And regression analysis is one of those things. Well, I'm not going to go there. But we have the covariance. Covariance is covariance measures the is a measure of when X deviates from its expected value and Y deviates from its expected value, you multiply these two together. If they tend to move in the same direction, so both are, when one is higher than average, the other is also higher than average. When one is lower than average, the other is also lower than average. Then if this happens, then the covariance tends to be positive. If they move in the opposite direction, so that when X is larger than its expected value, then Y is smaller, then the covariance tends to be negative. If X being high or low has no effect on Y being high or low, then there are as many negatives as positives, and they tend to cancel out. So the covariance is zero or close to zero. Sample covariance very seldom is exactly zero. We didn't talk about sample covariance, but just like you can do the sample variance, you can calculate sample covariance and sample correlations. Not going to go there, but just understand the analogous definition. Covariance, however, was not that much, I mean, they're not invariant to scaling. So if you multiply X with something and leave Y as it is, then the covariance increases if it's already there because of the way that the variance works. But if we normalize these by dividing X with its standard deviation and Y with its standard deviation, so these are the normalized variables which have variance of 1, then their covariance is called correlation. So the correlation is the covariance of XY divided by the product of the standard deviations of X and Y. And this is called the linear correlation. It's a measure of linear dependency between two variables. Have to understand that there may be a nonlinear correlation, one that would then be very differently defined. Very hard to come up with, but you know, machine learning things like that, they tend to be able to eke out complicated nonlinear correlations. So here are an example. Here correlation is 0.7, so we see a clear tendency of when X increases, X is large, then Y is large. Here we see a clear tendency that when X is large, then Y is small. Here we see a perfect line, or almost perfect line, then it's -1. And the idea here is that the correlation is 1 or -1 if and only if the probability of Y hitting exactly a given line is 1. So here's another situation where the correlation is 0 because for the average of, or the expected value of X is somewhere in here, the expected value of Y is somewhere in here, and they don't seem to have all that much correlation, but there is clearly a dependency. This is a nonlinear dependency here, and then you need nonlinear definitions to eke out this kind of dependency. Not going to go there, but then there's a lot of literature out there with social studies and socioeconomic factors and there where correlations are very small or close to 0, in which it has been deduced that they have no bearing on it, but when there might in fact be a curve like this. So not sure if it's true, but if you do the cross-country Well, no. Let me skip that example because it's not a good example for this. And so what I mean is, the bottom line, correlation of zero doesn't mean there isn't any dependency. It means that the dependency, if it exists, is not straightforward. We had some theorems about how the variance and the covariance have, what kind of a connection there is and so forth. Not going to go there. Independent variables, their variances add up. For dependent variables, the variances add, but then you have to fix it with the covariance. This is a very powerful tool for many situations. I gave an example, and I'm going to give the same example now. Let's say you are investing, and you have a possible investment where you have some expected value for the for a certain let's say that you are let's say you are investing you are going to invest in two different assets, and they will generate a certain profit, these investments. But the thing is, you want to make sure that your variance of your profits is low. And if these two assets have a high correlation, positive correlation, that if you invest in both, let's say half and half, then the variance is okay, half and half, and you notice that if the covariance is very high, then this will add to the variance. If the covariance is zero, then investing half and half gives 1/4 variance of X, 1/4 variance of Y. So this should be lower than the variance of investing only in one. It gets even better if the covariance is negative, because then if you invest in them, then your variance, you get this half and half, quarter of the variance of X, quarter of the variance of Y, plus something negative. So the variance goes down even further. So the idea is that you can hedge your investments, meaning that you can decrease the risk. This is not definitely something that works 100%, but it's definitely it's something you can look up, the so-called capital asset pricing model, if you are interested in this part of application of variances and so forth. It's a fascinating thing. There is several, it's based on generalization of this formula from a formula like this, where they're not independent. So you have this plus then some corrective factors based on correlations or covariances. Not going to go in depth there. So you optimize to minimize the variance and maximize the expected value. One important concept is the Chebyshev's inequality. I was going to say powerful, but it's not really a very powerful tool. It gives you a absolute limit to the probability of certain very uncommon events. So if you have this applies to any variable that has a meaningful variance and expected value. So by this time, you should be aware that there do exist distributions that do not have expected value or variance. Well, expected value or variance. There may be distributions that do have an expected value but no variance, because the variance is based on the definition, the variance would be infinite. So Variance tells us how far from the expected value the random values tend to be ending on average. So if we don't know how the density function works, we can come up with at least a rudimentary limit. So in particular, if we have standard deviation sigma, then the probability of ending further away than k times sigma from the expected value cannot be more than 1 over k squared. So whatever the variance or the standard deviation is, ending up further than 10 times the standard deviation from the expected value cannot be more than likely than 1 in 100. So, you know, this gives a very pessimistic view. I mean, the sort of, you can look it up, you can find it on Wikipedia. There's an example of a distribution where you can come up with distributions where there's a small amount of probability mass at the edges, and you put it further and further away, and you arrive exactly at this limit. You can look it up, you can find it there. In the case of a continuous random variable, we can prove it fairly easily by a simple manipulation of the formula of the probability. So we integrate over the area, f of x times, so f of x is integrated over the area. And then we notice that in this area, this quantity x minus mu squared over t squared is going to be greater than 1. And then, you know, this way you get the variance here, and you come up with this variance over t squared. Here were some things that we used. So, you know, things would look radically different if we couldn't make the normality assumption, if we could only rely on the Chebyshev inequality, because the alpha, the risk level, you know, we would almost never reject the null hypothesis if there's a significant randomness involved. Moment generating functions, not going to spend time here. This is akin to the Laplace transform, very much used like the Laplace transform. It gives us tools to analyze the distribution's properties using advanced calculus. I'm not going to go there, and really not worth spending too much time on that. This is for those people who are more interested in the hard mathematics side of this, and definitely, you know, gives you something to expand your consciousness with, if you want, if that's what you are looking for. You know, just say no to drugs, do hard math. Random distributions, we talked about this. It's a little bit bad, this here, but we talked about the sample variance. We defined the sample mean and sample variance. So if we take a big sample, we get these two statistics, and most of the things that we calculated from these. So the thing to understand is that if you have vectors, you could just as well calculate sample covariance and sample correlations and things like this, and no biggie. Here we had some ideas about how to deal with statistics. We had MATLAB, that mean x and var x we often had with this, help with this. Then we talked about the Bernoulli experiment in the binomial distribution. This is really important to understand that this we talked about a little bit differently. Binomial distribution comes to play in the beginning or also, but here we kind of grounded on the idea of the Bernoulli experiment. This is like, you know, how many people were watching a certain TV show, and we come up with the probability of a person watching the TV show, and then we take a sample and we get a binomial distribution where each of these is Bernoulli variable. This is very often used in simulations and things like this. I'm not going to go in depth in detail here. Distributions, properties here. Here were just some examples. Here's a Poisson distribution. This was a situation where we had a parameter. The Poisson distribution was a discrete random variable. So it measures really the occurrence of certain things over time, where the time frame can be larger or smaller. And then this lambda is how many per time unit. It doesn't have to be time, it can be distance. So, you know, how many potholes on a kilometer of road, how many, how much, or how many weeds on a square meter of your field, and so forth. Those are the things that often follow the Poisson distribution. It was understood that if you think of this Poisson distribution as very, 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 very thin Bernoulli distribution or binomial distribution, where you have the n times p is fixed, but you press, this is the probability, n times p, that's the expected value of things that happening. If you do n trials, you get each time finding one, the probability is p. So let's say that it's the weeds on a square meter of a field. So let's say that you make the area that you look at so small that there cannot possibly be more than one plant on that region. So there's a probability p involved in finding it on that surface area. That's your NP, right? You do that many. But then, you know, you look at the limit where this NP is now fixed, but then you let the number of n go to infinity, and then you get the continuous version, kind of. It's like the continuous version of a binomial distribution, where this n is infinite and this n times p is fixed. And we come up with the limit of this binomial distribution as having the density function. That is the density function of the Poisson distribution. The convergence is very rapid. So here was with large n and small p, the binomial distribution is roughly the same as the Poisson distribution with n times p. So here, if we have if n times p is some macroscopic number in this case, then it makes sense to use the Poisson distribution. So let's say that if this is less than 1 in 100, less than or equal to 1 in 100, and this is greater than 100, then the difference is almost immaterial between the Poisson. The Poisson distribution, we talked about it a little bit, but there's a thing called the Poisson process. So the Poisson process has to have certain assumptions. For instance, that at different times or different intervals, the things are independent. So how many times it happened then doesn't have an effect on how many times it happens now or in the future. That's an integral part of the Poisson process. In the long run, this conforms to this Q, you know, this unit frequency, if you will, and that forms in the long run and also in medium run in some sense, that the longer the run, the closer it is to having a unit per unit Q, and it doesn't depend on where that long run is. The probability of that the certain event occurs in the very short run more than once is very low, approximately 0. So if you have an occurrence of something, then if you zoom in very close to that occurrence, then that's the only occurrence in that region. So I gave this example of the weeds on a square meter of a field. So if you zoom in very close to one weed, you know there will not be many more than one as long as your region is small enough. Because you can't have the seeds grow, you know, two different seeds. If they're too close to one another, then one of them will fail to grow, or some, you know, they will push each other apart, or something like this will happen. So when these assumptions are met, then what results in is a Poisson process, and then, you know, you can measure something here. So we had this example with the radioactive decay. How many particles happen to be emitted in 1 nanosecond? And I'm using here 1 gram of radium isotope because radium has about 1,000 years half-life. So if we are looking at intervals of a second or so, and even from that 1 second part, we just take 1 nanosecond, which is 1 billionth of a second. So the number of particles emitted is not going to change. It will change if we look at it for thousands of years, because the half-life is 1,000 years. So if we look at it for hundreds of years even, then at the end of the stage, it's different from the beginning, so it doesn't apply. But if we look at it for a few seconds or minutes, then that's not a problem. It's just such a small proportion of the whole material, you know. In this case, assuming it's a Poisson process, you know, the assumption is in the long run, but in the very long run, if you take, you know, in the long run, in this case, it means in a matter of seconds. But if it's in the long run, in the sense of thousands of years, then the assumptions are broken. So you have to be careful. This is just an example of a situation where you have a model and you have to think about when does the model apply. This is a situation where it doesn't apply if you just make the time frame too long. And then the ground jewel of everything here that we talked about was the very dangerous normal distribution. And now I say dangerous is that because when often we use these tools, we assume things are normal, have a normal distribution, and these assumptions seldom hold water, right? So it's very often the case where people make assumptions about normality, and then those assumptions don't work. Yeah. I once said that you know, there's no there is no such thing as normal distribution in the real world. And then another person said that, okay, well, they had some water droplets drop somewhere, and, you know, there was a process that is guaranteed to have you know, at the limit at normal distribution, and they had a pile of ice accumulate somewhere, very nicely a bell-shaped curve. And they said, are you claiming that that this didn't happen? And I said, I'm definitely not claiming that you had a pile of ice there, and I'm definitely not claiming that within certain tolerances, the bell curve, you know, the curve drawn by this normal distribution density function, pretty nicely fits your ice, the shape of the ice that's on your under your window. Definitely not claiming that. What I am claiming is that if you look closely enough, there's going to be differences from the shape, and it's not going to be exactly that. And that's how mathematical models work. So. There was a guy called Anatoly Butkovsky. He was a control theorist / mathematician from Russia. He used to give us lectures in the summers when it was still known as TUT. And I attended his seminars a couple of times. He touted this thing called the 100% law of effectiveness of mathematics. I don't believe it, but he said that, you know, for every natural phenomenon, there is a family, parameterized somehow, of mathematical models such that, you know, one increasingly more accurately describes that phenomenon, and at the limit there is no difference. The limit of the error goes to zero as you take a better and better, you know, more and more refined models of the phenomenon. And he had a converse of that, so that for every sequence of such models that converge to a reasonable function describing something, there is a phenomenon that is described by that family of models. I don't subscribe to this view as such, but it was a fascinating idea. So he lived for the mathematics that he was working on, and he had this strong belief that he was working with something that is not just close to, but of the essence of the whole universe or whatnot. I have no such delusions of grandeur myself, or maybe I'm just being a cynic, but these are useful tools, these tools. And normal distribution is one. It's mathematically very pleasing, especially due to what we call the central limit theorem. The central limit theorem, which states, just going to go there. That for any random variable that has a variance at expected value, the standardized sample mean approaches the 0-1 normal distribution. This is a mathematically pleasing. It's philosophically, how should I call that? Seductive. It's seductive. That's what it is. In making assumptions about normality everywhere. Because the thing is, if you have some phenomenon and you know there's a lot of things affecting it, so it's an average of many, many things, then you will be inclined to believe, especially if you take the other version here, which says that, did I have it here? This one. So that if you have an infinite sequence of independent random variables with variances and expected values, and with rather general assumptions so that these do not depend on each other that much and so forth, if you just take the sum of these variables divided by then the fixed variance there, or the standard deviation, then it also approaches the 0-1 normal distribution. So if you have many things affecting, many small things affecting one big thing, then you would assume that one big thing is normally distributed. So this applies to surprisingly many phenomena in the real life world, like height. People's height tend to be pretty well normally distributed, at least in regions that are at close to the medium. The mean. But of course, at the edges, it all breaks down. You see that the limit cannot be, I mean, you cannot have people shorter than 0. You cannot have, you will not have people taller than 5 meters. It's just not going to happen. But if you look at it very close to the a mean height, then it does look a lot like it's normally distributed. And you can say or explain this by the fact that, you know, every day we are exposed to certain different nutrients, different environmental factors that may affect when we are a child growing up. then we get daily different foods that affect how our bones grow. We get different amounts of sunlight to affect the amount of vitamin D. We have several genes that we have inherited from both of our parents, each of them giving their own random contributions to how tall we become as adults. We suffer random injuries every now and then, and so it's an average of many factors, many things, and then that's why it looks like it's normally distributed. Also, the binomial distribution, when you increase the n and keep p fixed, starts to look like the normal distribution with probability NP and with expected value NP and variance NP times 1 minus p. For similar reasons, it's a fact. You add many things that affect it. So you take the Bernoulli experiment and you repeat it millions or hundreds of times, then out comes a nice curve that looks a lot like the density function of the normal distribution. Then we talked about the sample variance and sample how it behaves. So we came up with this formula where the expected value of the sample variance is in fact the variance itself. And we came up with the proof that the sample variance is a random variable that conforms to the chi-squared distribution with n minus 1. Here it was n, but you know, n minus 1 when the sample variance over a sample of n, then it has chi-squared distribution with parameter n minus 1. The thing about that was that if we add n 0, 1 normally distributed variables, we get a chi-squared n distribution. In the sample variance case, we had n variables added, but the thing about that was that because the there was in the proof there was a little bit of a jump there. So this one here would be chi-squared and distributed. Each of these ones would be chi-squared 1 distributed because it's just, well, it's just the square of n0, 1. And we're subtracting this, so we're in, this is a bit bad proof, I give you that, but we're kind of subtracting one of this. So we're leaving one of them out of this equation. In some sense, we are, this wasn't a very good proof, I must say. I picked it up from a textbook and I left some corollary or some part that was there before, so I didn't want to. But the idea here is it's not that important, the technique here. The important thing to understand is because this already has 1/n of each of these, so you really have n minus 1 independent variables here. That's why it's n minus 1, not n. We talk about the confidence intervals. Those were just defined as you have some level alpha, and 1 minus alpha confidence interval is, 95% of the cases the estimator falls in this region. So that you have to understand that this is the estimator here is these endpoints. That's the random variable. The random variable is this interval, and the probability that this interval will land in such a way that the actual parameter is between those numbers, that's 1 minus alpha for any given theta. So it does not mean that it is 95% chance that the actual variance or actual expected value is between these two numbers. It's just that 95% of the time, these numbers would have been such that the actual number is between them. So just, just to give an example, if we roll the dice and we come up with a six-sided, let's say that we roll the two six-sided dice and we add the numbers. So this is our random variable, is the two die roll. So we get numbers between 2 and 12. And in 1 out of 18 cases, we get either a 2 or a 12. 1 out of 18 cases. And let's say that we are looking for the, what does that translate to? Something like 93%, 90, something like that. Let's say 93% confidence interval. We roll the die several times and we calculate that value. And usually we get numbers that are somewhat, somewhere over a bit over 2 and a bit under 12, the ends of the confidence intervals. But then, sometimes we get values that are higher and lower. So sometimes the 2 and sometimes the 12 is included there. This is probably the beginning of what I said. You have to think in an inverted manner. You have to think in terms of what the probability is. So beforehand, when we have defined the confidence interval, how we are going to calculate it. So before we make the experiment, we know if we assume that this is our distribution, let's say it's a normal distribution. We're going to make the experiment, we're going to gather the sample, and we know how we are going to calculate the actual confidence interval. So in this case, for instance, the confidence interval for expected value. So we define it as, we are going to define it like this. There is a random effect here from calculating the sample average. This is an unknown. And then once we have the sample average and know the sample size, we get these endpoints. So before we have calculated anything, we know that, let's say alpha is 0.05. Then before we've calculated the sample, we know that if our variable is normally distributed, or n is very large, and we know that the variance is this, then 95% of the time we will end up with a number like this in such a way that this mu is between those two numbers. 95% of the time. So in 1 in 20, we end up with an interval where the expected value is outside that interval. So the confidence, 95% confidence interval becomes that we are 95% confident before the fact. But after the fact, who's to say? And then there were these different confidence intervals, and really these same formulas were used when we talked about the, so we need the t distribution here, and we wanted the t distribution we needed when we didn't know the variances, that we had to resort to the sample variance or the sample deviation. Then we use the t distribution. And then when we talked about the variance and we divide the confidence interval for this, we needed to use the chi-squared distribution. And the thing to understand is that the statistical testing works exactly like this. You come up with the confidence interval for your random sample, and then if your confidence interval does not contain the value you're looking for, then you reject the null hypothesis. That can be thought of in this way. It's a little bit different, so don't get hung up on, don't try to derive it from that, but it's really, you're using the similar formula here. This. And this was our null hypothesis, that this is the if this is either above that or below that, then we have a problem. We have a problem. We don't have it inside the confidence interval. The hypothesized value is not inside the confidence interval. All right, and then the testing, you know, if you look at this testing, it's defined in a similar way, but this testing framework here, the idea here was really that we assume the null hypothesis to be true, and then we calculate the sample and we look at whether it's within confines of the significant, you know, the critical region. If it falls into the critical region, we reject the null hypothesis. And you really have to understand how these how to derive this, come up with a justification, whether you're using the one-tailed or the two-tailed test. This was the latest things we covered, so I'm going to just skip this because we had a lot of examples here. Yeah, and then the final test was the F test. This doesn't have a confidence interval associated with it because, you know, this is a comparison of two sample variances. So we go up with a distribution for that. All right. Okay. So this concludes this today's lecture, and this was just a recap of the things that we discussed during the course. I tried to highlight the important parts. There will be, I mean, I already posted on Moodle the idea of the mock exam. So you can try that. That's it. Now it's just questions from week 5. So the idea is not that mock exam. It's just that you can try whether you can submit something in there. And I will look at that and mark it as done if you have done it. And so I know that you can do it. So answer, you know, doesn't even have to have the answers to that, but submit a PDF file that contains something that is supposed to be the mock answers to that. And if that works nicely, then everything is fine. If you can't submit or you have some problems, then drop me an email immediately and I will check how it works. So how it works is that on May the 6th, on 5 p.m., the questions of the actual exam will appear in that, below that mock exam. And you have 3 hours at that time to do it, by any means you wish to use. It's an open book, no holds barred, all software allowed, nothing forbidden. But you have to come up with the answers in that 3 hour time period, and come up with answers of your own. I won't consider cheating of any sort if you have used some software or something like this. What I will do, however, I will check every individual answer against one another. And if I see that people have made identical mistakes or anything like that, then that will have consequences. That I consider cheating. So do it yourself. That's the only thing. Do it yourself using whatever material you have, and don't copy someone else's answers. I'm not going to monitor it. I'm not going to do any police work on that. What I am going to do is I'm just going to compare these documents with this software to one another. If it's not susceptible to using the software, what I'm going to do is I'm going to do it by hand. There's only if this all looks like it looks, there's going to be 35 of them, then I will notice if you've submitted the same answer twice. I mean, if two people have submitted the same answer, so don't do that. Put it on paper and scan it and send it as PDF, or write it directly into a text editor and export as PDF. Anything like that goes. There will be something that might require you to use MATLAB, but all those questions will be such that you can answer them using just the tables, the T tables and the F tables and the chi squared tables. I don't know if there's an F table now if there's not, then I will add one. I will update the mock exam questions in such a way that they will be similar in format to the questions in the actual exam, so that you will have some idea of what to expect. Okay, I'll add the F table there. Thanks, Al. I'll add the F table on Moodle. If at this time you have problems and you don't know how to use MATLAB, you don't have MATLAB at your disposal, now is the time to make sure that you can do that. I'll send a message about this is also on Moodle. I hope we can come up with a reasonable way of getting through this. Yeah. So are there any questions now? So this is the final lecture now. Tomorrow I will add the workshop and questions for the missing, for those who have missing exercises from missing weeks. You have missed some exercises from weeks. So the idea is that that last workshop, I will review it myself. And no, in fact, no, I'll put it on review, but I'll put it more I'll put it on peer review as well, but I will monitor it a bit more closely, because yeah, you can do it. You of course, definitely you can do it. But my point, good point, Anton. You can always do it with MATLAB. You can find the FCDF and FINV from there. The thing is, if you don't want to use MATLAB, if you want to look it up from the table, then I want it to be possible as well. I do encourage you to use software, MATLAB or any other such software that you might wish to use. I've used MATLAB as an example, and I've only covered the MATLAB commands, but I do firmly believe that still at this time and age, even though the skill of using software is of utmost importance, it still should still be possible to do it by hand, pen and paper. All right, I'm going to stop this recording now, unless there are any questions. Okay.